So yeah, welcome everyone to the second and final keynote of the Causal Data Science Meeting 2020. I'm very happy that we have Elias Bareinboim today giving the keynote. Elias is an associate professor at Columbia University. He's there also the head of the Causal AI lab at Columbia University. He holds a PhD in computer science from UCLA and was actually a student of Judea Pearl at UCLA. After his PhD, he moved to Purdue University, where he had a joint appointment at the computer science and statistics department. And yeah, it's fair to say that Elias' research has significantly pushed the boundaries of the graph-based approach to causal inference in recent years. Just some of the topics that Elias has worked on: Z identification, selection bias, methods for tackling transportability and external validity problems. Causal reinforcement learning is a very interesting line of his work. Elias has also papers on the big topics in AI, which is fairness and explainability. And I think we will see a lot of that popping up in his talk today: Causal Data Science, a general framework for causal inference and data fusion. Elias, I'm very happy that we have you here. And yeah, before I give you the floor, I should say we agreed on like roughly 60 minutes talks, and we will take questions afterwards. We have plenty of time, 30 minutes for Q&A afterwards. Would be great to get a good discussion going about causal inference in an applied setting. And yeah, that is from my side. And Elias, the floor is yours.
Cool. Yeah. Thank you, Paul. Thank you, the organizers, for the invitation. It's a pleasure to be here. Good afternoon or good night for some of the folks there. Today, I'm very happy to be here also because I'll talk about causal data science, which seems to be the name of and the topic of the workshop. I'll present kind of my view or my feelings about the foundations of CDS, and how you do inference, data fusion, how do you think about the problem of generalizability of causal knowledge or causal effects. I'm a professor at Columbia University, and I'm part of the Causal AI lab. As Paul, I also like to tweet, maybe a little bit less, but I try my best. Then there are always good discussions there. If you are interested, follow me, and I will be happy to talk with you. Or you can drop me a line by mail, it's fine as well. Then I would like to start with some different views of what could be aspirations and the challenges of causal data science or data science first. And I would like to start with a quote from Hal Varian, a chief economist at Google and a professor at UC Berkeley. He said, the ability to take data, to be able to understand it, to extract value from it, to visualize it, to communicate it. That's going to be hugely important in the next decades. Now we have Gary King, a professor at political science and statistics at Harvard, saying that big data and data science is not really about the data. and I'll try to elaborate. And then it comes Yuda Pearl, professor at computer science and statistics at UCLA, saying that data science is only as much of a science as it facilitates the interpretation of data, a two-body problem connecting data to reality. Then you have the first quote saying that it's all about the data. The second one saying it is not really about the data. And the third one, Yuda, saying that neither is kind of something about the connection between the data and this outside world that the data is being collected. Then I would like to and that's kind of beautiful and encodes different views and reality. I would like to start with a report then from the trenches, going a little bit less from this 20,000 view for what's going on in reality. As a soldier here, a data science soldier. This is a quote that I got from CNN saying that there's a study that heavy coffee drinking in people under 55 linked to early death. There's an interesting quote because we use this keyword here, linked to, in the sense that we do want to suggest, or to say in reality, not to suggest, we do want to say that there is some causal effect from heavy coffee drinking. Perhaps I'm in this group. And get my sip of coffee here. There is some kind of causal link or causal effect from the coffee to the early death. But at the same time, you are kind of shy or a little bit scared to make the bold statement. Otherwise, you'll be, how did you get the causal conclusions? Under what conditions this is true? Which kind of randomized control study did you run? And so on. Then people is kind of playing lawyerly, kind of playing a lawyer game here, and that kind of trying to phrase that you suggest that there is a causal effect, but at the same time, you're not claiming it. Then it's kind of defensible. You cannot be sued for making this suggestion, given that this link to is just a generic type of wording. Now I have a more subtle message saying that about, if you read about the relationship of coffee consumption with mortality in the annals of internal medicine. And by the way, I was just Googling at random. If you do your talk, you can just Google and you'll get many of these kind of headlines. Now something more interesting, I cannot sip here my beer at the moment. Even though there is this type of news saying that alcohol causes 20,000 cancer deaths in the US annually, which seems to be a quite devastating kind of piece of news. But now there is some kind of a little bit more positive, saying that one drink of red wine, I also enjoy, or alcohol is relaxing to circulation, but 2 drinks are stressful. Then it's not all bad about the 20,000 deaths, but perhaps there is some kind of threshold in here that maybe we are allowed to have a little bit of fun. Being responsible here for the kids in the room, or more than 21. Now I have something very exciting that's saying that why do heavy drinkers outlive non-drinkers? Then people should be happy. Then if we are in the group here, then it seems that is whatever, again, a good piece of news. Again, then you move from something that was catastrophic to something that there is a threshold, to something that perhaps I should just start drinking just after give this talk. Then I can go on. My last one here, this is in the New England Journal of Medicine, about the association of nut consumption with total and causal specific mortality. This is kind of nuts. This is why I like also this literally. It seems, and I could go on, and there is something about effect of grapefruit, or every time you have about the effect of red meat, or some type of egg. And I'm just in the domain of public health here. In economics, we could go like that. And the point here is, like, if you read this piece of news, by the way, I pick on purpose the New England Journal of Medicine. This is kind of the best, if you're in the medical field, the health field, the best and the brightest of the generations are trying to submit and get in their papers in this venue. Then, and the point that every X number of years, maybe 2 or 3 years, you have a flip or a different conclusion of what these studies are saying. Then the question for us as just consumers of causal information would be, what should I believe, or how do I take this seriously? And as producers, as scientists, data scientists, the question is like, what's happening here in reality? If the best and the brightest are having this type of challenge, under what conditions could you even get some kind of reliable and minimally believable causal statement? Or what's the difference between what we are doing and people that are with astrology, with all the respect to my astrologist friends, or alchemy, given that there are not many nowadays, I can say perhaps alchemy. And for sure you could, usually I ask, what are the other examples for your own research or on your own business setting, if you have this kind of situation. Paul, let me ask you a question. Someone I think I see that is raising the hand. Should I take the questions along the way or later? What is the protocol here?
I think it would actually be easiest to take questions afterwards, because then we can unmute people, and maybe if there's a clarification question, people can put it in the chat, and if there's really something urgent, I can read it out to you.
Okay.
Does that work?
Works for me. Works for me.
Then let's go like
and
this.
I think then guys, if you have a clarification questions, put in the chat or just scream. We'll try to get it. Otherwise, leave to later, given that we have half an hour for chatting later. But now, and the question that again is, what kind of examples you have in your own situation here? I'll be curious. Perhaps you can spend a little bit of time discussing that later on, and I'll be curious what happens even in the previous day. Now, again, the bottom line question here is like, what's going on here? How is this possible, right? And after all, is it possible to get causal conclusions from whatever type of data collection you have? Why is this happening? Now, my take is like lack of data, my view, lack of data fusion capabilities. I think you don't know how to do data fusion properly, or it's too recent technology that we have, then people is just messed up. And the whole talk would be, I try to elaborate what this could mean, even that is a very generic type of sentence. Now, the goal of the talk, let me be upfront here, would be to develop machinery. And what I mean by that is language, conditions, and algorithms for performing data fusion about population level interventions by cohesively combining multiple heterogeneous data sets. If you want to talk about individual level, ask me questions later what I think about that. But anyhow, at least in the beginning, we would like to do at least population level interventions. All statements that I got from the news there are about population level, averages over the populations, the corresponding population. Now, this is our goal, develop this type of machinery, again, to perform infusion from population level interventions by cohesively combining multiple heterogeneous data sets. There are so many papers about this topic, or starting to grow in literature on the topic. This is just the reference that kind of motivates the talk, is the paper in the Proceedings of the National Academy with Yuda Pro himself, that kind of summarized the state of affairs around maybe 3 years ago. Many other papers if you want more recent literature. In particular, I put Paul's picture here. You see, Paul, you're with your mustache. This is a recent paper. I'm doing advertisement here for you. But it's a very good paper, by the way, jokes aside. It's a paper that Paul and I are writing for some time now on the causal inference and data fusion in econometrics. I would say econometrics in business. That is kind of an enlarged version of this PNAS paper. I think we are very proud of the result. We are still trying to get feedback from people. If you have a chance of reading, I strongly recommend it. If you have a chance of reading the paper, please drop us a line and share your thoughts and recommendations. But anyhow, it's a kind of tour de force about the most modern results on data fusion. Now, then what's the challenge here? And I put data, and the key observation here is that, or the challenge is that all data is not created equal. And what I mean by that is that there is a lot of data out there, and everyone is excited, including me and Paul, I'm sure, but the data is almost invariably collected under different experimental conditions. The underlying populations are different. The sampling procedure is not always, or is rarely randomized. The treatment assignment very frequently is not randomized or controlled as well. And many variables are not measured, or they are not measured consistently across the studies. We have different columns in the data sets that we're collecting. Now, in other words, the premise here of our work is like the data collection, or the data that we collect, is messy and very rarely matches the inferential target. Meaning, that's the premise. Some people, common confusion here, parentheses, some people believe that everything to us to do, things need to be perfect, or under the real world, when things are messy, perhaps it doesn't work. Quite the contrary. If everything is perfect and clean and nice, and we don't have any of these dimensions here, I listed 5 important data fusion dimensions, we don't need me, you don't need Paul, we don't need anyone to do data analysis. We're doing counting. We can put whatever, make a monkey in there, or machine learning, or a standard kind of statisticians, just doing counting and doing empirical, density estimation. Then no need for anything that we discuss, Perl, and so on. The whole point of everything that we're doing is when things are messy, and there is a mismatch in the data collection between what we collected and what we are trying to infer, which I will elaborate. That's the challenge. The positive here, because this seems to be very tough in some ways, we're operating under this kind of darkness or partial observability, if you want to sound technical. The positive here that all these dimensions that we have above are now formalized. Then first step to solve a problem is to have it in some type of formal language, some type of mathematics. And also another piece of positive news is that there are conditions and algorithms to decide what is quote unquote entail, or what we can inferable from this certain data collection that we have. Now let me elaborate a little bit more about these dimensions, and what is a data collection. So what are these heterogeneous data sets? Suppose that you have a target quantity, P star of y given to x. And what I mean by that is like, I like the causal, after 2 days, I think you heard this do x operator, but is the causal effect of assigning this treatment x on the outcome variable y. For sure, this is in contrast in the population pi star. This is why I'm annotating the star. I would add the non-star later, but let's be positive here that we're talking about stars. And astrology and astronomy in reality better. But this is the target quantity, P star of y given to x, effect of x and y in a certain population star, or pi star I call. And we are trying to contrast that against the prediction of P star or P of y given x. Then that's the tension between prediction, that is the one in gray, in orange, versus the causal, the predicting the effect of the intervention. The latter, or the one in orange, is about if I'm just playing a game and I want to predict if the person will recover. If I see the person getting or not the treatment, or getting or not the advertisement, then this is whatever, the orange here. But on the other hand, if I want to decide if I should submit this person or this group of the population to this condition, then that's the first condition in white there, P star of y given to x. Now let me remove the prediction here, given that we're in the causal business. We don't want to do prediction. But just one more note here. If you read Yuda's Book of Y, strongly recommended Book of Y, the one in orange is the layer 1, or level 1 of the ladder of causation. I like to call pro-causal hierarchy. And the second one, y do x, is layer 2 of the PCH, or the causal hierarchy, pro-causal hierarchy PCH. Right now, close parentheses here, sorry for the tangent. Our goal is to chase this quantity Q is equal to P star of y given to x. Now what we have there, we have different data sets, data set 1, data set 2, and so on. Now, what do I mean by these 5 dimensions that I just described? First dimension, data is collected from different populations. For example, the first data set could be from LA, where Yuda Pro is there. The second data set is from New York, and so on. The last data set is from Texas. We have the Copenhagen data set from Paul. He is also part of the study, and so on. Now, this is the underlying populations are different. What's the second dimension? The treatment is not necessarily randomized or controlled. Then perhaps you have this sometimes as observational, such as in New York as observational study. You don't have any controllability, or you didn't randomize the treatment assignment. On the other hand, the first one here in New York, the first data set, the one that is coming from LA, is experimental. Importantly, people also usually miss that. Paul mentioned the ZID, but it depends. Whenever it's experimental, we need to know what was randomized, because I have 100 variables in the system. Maybe it matters that, for example, in the first data set, what was randomized was Z1. Note, in other words, you have this do Z1 kind of data set. In reality, our goal was not to get the Z1 from LA. In reality, we are trying to get a population star, the do X. Then you already have a mismatch there. Still, the system is submitted to randomization. This may be useful in some way. Second dimension was, again, just to conclude or to summarize, observation or experimental, and what was randomized. Third dimension, selection. Perhaps there is the data that is coming from, say, from New York, there is a selective pressure on socioeconomic status. The data that is coming from LA is there is a pressure, or age affects the probability of being sampled. Perhaps we are doing, or just in context of election, we are doing some polling. Maybe people are doing polling by calling landlines. Then, yeah, people may be less than 30, for sure, even maybe less than 40. They don't even have landlines, or very rarely. Then, for sure, they will be underrepresented in the samples. This is the third dimension. The sample is not representative of the underlying population. Fourth dimension is like the measurements are not consistent across the populations. For example, in the first, let's say that this is time series data, then you have the treatment X1 and the outcome Y1 in the first time slot. Now, on the other, and maybe you didn't measure the second time slot, that is X2 that you have in the second data set. In other words, again, the columns of the data sets are not the same across these different studies. And those are the dimensions. Now, keep these dimensions in mind, because I would like now to connect the dimensions, what we have been doing for a long time. Someone is talking here. Andres, is this the question or not? Should I ignore? Create the whole polynomial.
We can take that later on.
Okay, okay. I will ignore then whatever is being written here in the chat. I would like to connect these dimensions, as I said, with things that we have been doing all along for a long time, just to seems from other universe, not really. This is exactly what we have been doing. Then let me put in context the dimensions and tasks that you have in data fusion, or as I say, some common inferences in scientific circles, AI and machine learning involving standard assumptions. Now, what are these dimensions or tasks? For a long time, we have been doing, I need to go over that, sorry, but we have been doing descriptive statistics. What was the big deal in descriptive statistics? I mean, this kind of arrow here, why it took maybe a few hundred years to us to understand. In reality, it's a big deal because this is an induction problem. We are moving from a particular, that is the sample, that is finite, to make a statement about an underlying population. Then the whole challenge is this arrow here. It took us maybe 200 years or so to prove some things like law of large number. This is this arrow here. Law of large number, central limit theorem, data method, some type of guarantee that this kind of sampling that we are doing, the data that we get and the procedure that we get through this sampling eventually will match this underlying truth that is usually unmeasured. There is some kind of feel good or some type of theoretical guarantees that what we're doing makes sense. Then this is why I took, and I attribute that to Bernoulli, just a few, Poisson, Kolmogorov, and so on, to understand and put that in solid foundations. Now I have a second dimension. It took also maybe 100 years, and since maybe statistics, or 50 in reality, but since statistics came about, at least officially, to us to move to the experimental side from Fisher. Now we are no longer just talking about, he was the one to realize that we're not trying to talk about OBS, but we are trying to talk about sampling when you submit the population to this condition, when we introduce the randomization of the treatment assignment. The high tech of the time, or the AI of the time, this is high tech now, but the high tech of the time that Fisher was studying was agriculture. And we have some kind of problems of confounding related to the assignment of the pesticides by the farmers. But anyhow, we can read a little bit of history, but the point is like he has this ingenious idea of introducing the randomization of the treatment assignment. Then I attribute this idea, and I mean by this arrow here, we attribute this idea for Fisher, Cox, and so on. Then we understand pretty well, now any university will have a course on experimental design that's exactly following from these ideas. There are a lot of technicalities. It takes a few years to understand and crack all the details, but fundamentally started there, at least as I read history. Now come a new animal in the zoo, I usually say, I like to think, that is causal inference. Other animal, because it's qualitatively different than what we were doing before. What do I mean by that? Before, note here that the inference that we are trying to do is from sample to distribution. And difference between 1 and 2, one is observational sample, the other is experimental sample. Then he introduced the concept of having the regime, the experimental regime, Fisher itself. Now, again, don't get nervous because this is my reading. Some people may have different opinions, and this is totally fine. This is just a protection statement here. But causal inference is different because now we are trying to go from the distribution that is OBS to the distribution that is experimental. Then, in other words, from this distribution here that you collect, suppose that you collect the data that is OBS, you did pretty well, and this arrow here worked. Maybe under the limit, we ended up being able to, in the best case scenario, you are able to get this one. But now we said, oh, I didn't care about this one, really. I'm trying to get another distribution that I don't have any samples from, for example. And this is why how causal inference started. We are trying to move across distributions. I just connecting these two, or kind of in this way. For sure, it relies on 1 and 2, or a combination of 1 and 2 dependent. Everything relies on 1 and 2. We're kind of building. That's what's data fusion. Now, this is my reading again of history. Don't shoot here. But causal inference from around 74 and 74 was mainly concerned about confounding bias. What is confounding bias? That you probably heard these terms. Confounding bias is nothing more than the difference between this guy, or this P of y given do x, minus P of y given x, that is this one here. This is confounding bias. I would say obsession here from the causal analysts for 40 years, almost 40 years. And this has been essentially solved. In other words, you understand pretty well, this is why I put this arrow, under what conditions can you move from the left side to the right side. And by whom? By starting from Rubin, you get Robbins, David, and Pearl himself. I'm not giving a class here on my usual class. We'll go over the details about what each one did and how they connect in some sense. I will no point in doing that because all of them are solving this problem here. But I do attribute to Rubin the first to connect. For sure, is a name on Rubin thing, but Rubin was the one to connect these different regimes here. I think it's quite important to give the credit, given that it was such an insightful and important idea. But anyhow, that's the summary here, what's going on. No credit here, and you are giving credit for the who credit is due. Now, usually question here, usually people ask, Elias, are you saying that we are done? Because it seems that you are covering the whole ground here. And also, I also get the, Elias, those are all, whatever, I'm phrasing my way, here's my reading, but here's those are known things. This is kind of old stuff, some people tell me. When does causal data science comes into play? Then I'll try to answer this one. But now I have the context. Now I will apply a trick here, computer science trick. Now I would like to get these 4 dimensions that I just described. That is, what is the population, is observational or experimental, what is the sampling, and what was measured. And I would like computer science trick. I would like to parameterize these problems here, or this class of inferences in terms of these 4 dimensions. Let me do the magic here, done. Now, note here, let me pick one of them, that is the causal inference, for example. Here we are saying, or the inference that we have allowed, or the conditions that were studied before, is assuming that we are talking about the one that is the same population. You are talking about the sampling worked, that you are representative, and we are talking that what measured work, that is D4 is equal to D4 here. Now, this D1, D3, and D4 are fixed. What we are doing in this setting is to move from OBS to do X. I just put in the notation of the dimensions, data fusion dimensions. Now, and you can do the same here for these others. Now, let me, again, the question will be, do these dimensions exhaust all possible data collection modes? And the answer, I just copy here the previous one, the last one that is the interesting. And I would say, no, they don't exhaust. And I would like to show the others that I discussed. For example, there is something called I like to call experimental inference. Some people call generalized instrumental variables. Paul likes the ZID. This is the idea of, suppose that the type of inference that we are trying to do is we collected data over where a variable do Z was randomized, and in reality, we are trying to make an inference about as if you randomize the do X, the variable X, which led to the do X. Now, this problem has been studied for a long time. Again, you can discuss credit here, but by the father and son called Philip and C.O. Wright. There's a huge, interesting history about who did the discovery. I'll put as both since the 1928. Given that I'm with people that do economics and business, I think IV is very well known, usually at least in the linear or some kind of special cases, but that's kind of the anatomy of what IV is trying to do. Huge history, very nice piece of work. What's the other dimensions, Elias? Let's move to dimension number 3. Dimension number 3 is called sampling selection bias, or sampling bias by some people. So sometimes it's messed up with confounding. This is not confounding. Confounding is the first here. Now we're talking about sampling only, not the assignment, but how you collect, how you sample from the population. Here, assume that the dimensions D1, D2, and D4 are fixed, and now perhaps there is the selective pressure on age. And we'd like to know about the population without the selective pressure, in the same proportions that we have in the true population. Now, there's huge history of this problem. In economics, a professor at the University of Chicago, James Heckman, 1976, he has a work about showing under what conditions can you recover when your data collection is plagued with selection bias related to the reservation wage that you don't measure the wage of people that is not employed. There's a detail, a huge amount of work. For this arrow here, he got the Nobel, many reasons, but one of them related to this work to show the feasibility, my reading, right, of the Nobel, the feasibility of having a data collected that is messed up in this way. Maybe people didn't think that you could make the statement about the whole population. Then he showed like one instance of this arrow here that this could be done. Thousands of papers written after that to generalize the setting, but ingenious observation about it's possible. It was possible, that's not believable. Kind of introducing the problem in a modern way. People are discussing that for some time. Now this is sampling selection bias, the third dimension of data fusion. Another problem called transportability, or also known in the science as external validity. Here you fix dimensions 2, 3, and 4, and now we are talking again about the populations are not the same. This is how things are messed up. For example, perhaps you could collect data of bonobos, that's a type of monkey, and in reality, we'll actually make a statement about Homo sapiens, about us. Under what conditions this is done? This could be done. But maybe you have a study that is in Copenhagen and with the students and so on. Now we like to move that to the US or to New York, for example. Under what conditions can you do that? The bonobo to humans is a very challenging instance, but in reality, the same kind of problem, the same type of mathematics, the same class of inference, as we say formally. Problem have been studied at some degree, and semi-formal, usually I'll say, I attribute to the Shadish, Cook, and Campbell as classic on the quasi-experimental design setting. Oh, this is, thanks. This is from New York. Let's flip. We conducted, because New York is more liberal, maybe you conducted a study that was allowed here in New York, not that we are bonobos and the people in Copenhagen are the humans, but you collected data in New York because it's allowed to do the experiment, and now we would like to do the inference in Copenhagen because whatever, the government is more concerned and don't want to submit the population to these specific conditions. Now, this is the kind of inference that we're trying to do, to evaluate. Now, my observation here, EB, is like special cases of these dimensions have been addressed in the literature, mostly in isolation and under very special parametric conditions, like Heckman in some kind of linear model and Gaussian and so on. And all of them in reality, instrumental variables. And in practice, they appear together in what I like to call, or Poe and I should say, like to talk this causal data fusion. In other words, we have, this is brackets here to say that it's a collection, it's not only one data set. Now I have a collection of data set that is a tuple, this kind of 4D space, and we would like to do an inference in this star population when you have this particular D1 star, D2 star, and so on. And this is data fusion. Now, that's the big picture. Now I would like to discuss a little bit more in the second part of the talk, give a little bit more concretely one of these tasks. It takes like the whole semester to go one by one and discuss the results. I would just like to give you the flavor about what I mean by these type of conditions. Which conditions could be licensing that will allow us to do this inference. Then I would like to talk about transportability, or the extrapolation, another name in machine learning called robustness of the causal claims. How the causal claims stand when you start going through this changing conditions, when you move the agent across changing conditions, which is almost always the case, by the way. Now, let me start with the problem statement. Is usually people don't even agree with that. Very important. Question that we're research question. Is it possible to compute the effect of X on Y, a causal effect of X on Y in a target population pi star where no experiments are feasible, using experimental findings from a different environment or population pi? Answer, sometimes it is possible. And the whole endeavor is under what conditions this is possible. When and how can we do that? And what I mean by this when and how, I would like to use a metaphor. And the metaphor is, how do you move knowledge? It's true, but it's also more broad. The word of lab, from the lab to the real world. And the lab is this place, this dear and lovely place that I put small here, that have the relationship between X, Y, and Z, and W. And the lab is this place that you can go there and do all experiments that you want. I can turn the system upside down. I can perturb the system. I can submit the system to whatever condition we want. And by the way, lab here, as I said, or as I wanted to say, is just a metaphor to environment, population, domain, or setting. Now, lab is this good place. The data science is faced with the challenge about they don't care really about the lab. They want to make the statement outside the lab or in the real world. Then the challenge is like, what is the relationship between the lab and outside the lab? Then there's a hypothesis H1 here. But I forgot to say here, I assume that we already discussed that in the last days, but I'd like to recall, I think Carlos talked earlier, probably he talked about that, I would guess. This causal graph here is nothing more than the parsimonious or the non-parametric representation of this underlying collection of mechanisms. And it's parsimonious because we don't know exactly what is the particular form. This is why we are doing causal inference and we are not doing physics. That's the difference between us and the physicists. Now, in other words, this graph here in reality is coded in the variable z. There is this underlying mechanism f sub z, that z gets the value after passing through the f sub z, and a source of endogenous variation, exogenous variation, u sub z, let's call. There is a variable x here, and there is this mechanism f sub x, such that x or equal to f of x of z and another source of variation from x. Let's call u sub x. W is equal to f of w of x, it listens to the variable x, and another source of variation for w, let's call uw, and so on. Then the graph is nothing more than this representation, just a quick revamp here or recap. Now, the challenge at H1, the scientists need to relate how the mechanisms in the lab are related to the mechanisms outside the lab, in the real world, or RW as we call. Now, here, hypothesis H1, that the mechanisms are shared, are the same. In other words, the f of z in the lab is equal to the f of z star in the real world, the real RW. The f of x is equal to the f of x star. The f of w is equal to the f of w star, and so on. Now, this is hypothesis H1. Then, in reality, we're assuming that structurally, everything is assumed to be the same, then things are trivially transportable. You just get whatever result we have in the lab, and things will hold outside the lab. Now, break you the news here, that's too good. It's kind of pink world, dream world. Almost never, or to be honest, let me pause it. Almost never the case. It holds with whatever, mass zero. Now, but this is one situation, one possible inference. The other one that is the nightmare or the counterpart scenario is that relationship between what's going on in the lab and outside the lab is completely different. What I mean by that, formally, if you go to the mathematics, is like f of z is different than f of z star. F of x is different than f of x star. F of w, and so on. Now, if that's the case, it's kind of nightmare scenario. Everything's assumed to be different. Nothing is transportable. Then nothing that we did in the lab will hold outside the lab, which is kind of nightmare. It's also usually too strong. Usually not the case. Why? Usually you kind of learn things, the populations are not the same, the conditions are not the same, but we eventually are able to learn and evolve. And you keep kind of gathering more and more causal information. Then point here is like there is something in between these two extremes, kind of dreamish, nightmare kind of ish scenario, that is that will allow us to learn under under some conditions. Now I would like exactly to try to pick someone that could be in between these two extremes. One quick note on notation here. I'm not introducing it formally, but note here that this diagram here that I'm showing in reality is not the diagram in the target, is the difference or the overlapping between the diagram in the source and the diagram in the target, what we call selection diagram. And note here that there is, for just operating with one diagram, we annotate the diagram with this square or yellow type of arrow here, which means that in reality, the assumption that when we remove one yellow, which means that we are claiming that there is an invariance in one of these mechanisms. In this case here in the left side, we essentially, there is no yellow, even though it's a selection diagram or overlap, which are claiming that f of z is equal to f of z star, f of x is equal to f of x star, and so on. On the other hand, we'll remove, if you come to me and say, Elias, I know nothing about this thing. I'm clueless about this type of inference. Then what does it mean? You put the yellow pointing to everyone, which will imply that you cannot do any inference. It's provable the case. I can show, we can discuss theorems offline. Now, the assumptions are in the removal of the yellow arrows. Don't know anything, or you start the analysis with all yellows there. Now, again, closing parenthesis here in terms of notation. What we want to show you is like, we are usually not in this extreme situation. There is something living in between this case that allows us to eventually to learn. Well, let me pick one guy that is in between. What this could be, here it comes. The question that we're trying to answer is like, what can experiments in LA or in this UCLA hospital tell us about the Columbia Hospital here in New York? Now, to ground notation, you have the population pi, that is the source, that is the UCLA or call LA population, and you have the population pi star, that is the New York population. Now, you also have what is the selection diagram here, that is the overlapping of these two diagrams. Note here that we are in the middle. There is some yellow, but there is not only yellow. Not everyone has yellow arrows. What we are in reality claiming here is that the f of y is shared across LA and New York. In other words, suppose that we are trying to get the effect of some x on y, some treatment or some treatment in the outcome, could be any, some decision in the outcome, some reward, and you have the age that is also in the analysis. Here we are saying that after age is there, the maybe human biology is the same across LA and New York, and the f of y will be shared, will be the same. Maybe f of y is the biology, how people react to the treatment. That's the assumption here in this particular case. Now, this is the meaning of this diagram. Now, this is part of the input of the analysis. Qualitative understanding about how the population in LA and New York are related. Now, we also have quantitative part of the input. And what will be the quantitative? We have, as I said earlier, you have experimental study in LA. We spend, at least in the medical field, spend $3-4 million there, and you run our experiment in the UCLA hospital, which allows us to compute or to get this distribution P of y given do x for each age group, z, the z-specific effect of x on y. I'm just putting for free here that is usually easier to get the observational study in LA. Anyhow, this is the important one, is the P of y given do x for each age group. Now, what we have in the target, as I said, the target, we cannot conduct experiment, at least not in this particular instance. What we have in the target is observational study P star of x, y, and z. Perhaps the government here in New York doesn't allow the population to be submitted to this type of treatment. There's so many regulations here. Now, by the way, implied by this quick note, parenthesis, not the core, parenthesis, but implied by this z node here, the source of that f of z can be different than the f of z star, these will pop up in the data. We'll see something like the age distribution, P star of z is different than PZ. That's an implication, it's not a premise. Very important here that there is some clues that these disparities across the mechanisms in the two settings are generating some clues in the data that you can try to leverage, or we will try to leverage. But anyhow, input of the analysis or transportability analysis, qualitative understanding about the relationship between the population, and two pieces of quantitative input. One is experimental study in LA, and another is observational study in the target New York. What we want, or what's the output that we are aiming for? What we want is a quantity P star of y given to x. We're trying to get the causal effect of this treatment in the outcome in the New York population. Now, that's the anatomy here of the naked version of the transportability problem. If you understand that, we are already friends. I would like to talk more with you, because this is the main slide here. Now, it turns out that it's possible to solve this instance, to use this knowledge that we have encoded here, combine these two data sets, in order to answer this query here, P star Y do X, that you don't have any data. How do you do that? You do some type of reweighting, and the reweighting has the form that we get the Z specific effect of X on Y that is coming from LA, that is this guy here, and we reweight that by the new age distribution in New York. And you do that for every age group. This is the sum over Z for each age group. Now, the two comments here, this is what we're trying to do is to accommodate for the change in age in the causal effect. Because the causal effect is some type of average over each age group. That's kind of the general feeling. Now, second note here is that this is usually called, or I like to call the transport formula. That is exactly some type of function of how you combine the distributions that are available. There is this transformation F, that is in this case is this instance, to your target query, Q. Now, that's nice. And this formula here, first time maybe 2010, 2011, you have in a UCLA seminar, you have a demographer coming, attending the seminar when I first showed this one, and the guy kind of did like that and say, Elias or Yuda, but in reality, Elias, this is very nice and pretty, but we demographers know this, not in this notation, for more than 200 years. And he pointed to the paper of how people are doing that in demography related to accounting for some type of death rates and so on, morbidity rates. Now, and that was interesting. He said, oh, is your work useless? Or this is whatever. It was a very friendly seminar. Then it was a nice conversation. Now, the point that I want to make is like, it is true that this formula or variation, this formula, not in this form, is known for some time that we are trying to adjust. The whole idea of adjust is to account for the differences. The question is like, under what conditions this formula holds? Is this like a physical law that regardless of the type of data that you have, the population, the problem, the variables, this will be always equality? This is a universal law of the data sciences. Or are there situations that perhaps this is not true? If there are situations that it's not true, it means that they are just doing it blindly, which is this is from criticism for 200 years ago, folks. Then it's okay. They are no longer alive. Now, I would like to pursue this line to understand that if this is universal. In order to do so, I'll do the following. I just copy the previous graph that we have in the previous slide, and I added these dash bidirected arrows. Dash bidirected, that's nothing else means that there is some kind of unobserved confounder, in this case, U sub exogenous variable, U sub xz, that is both affecting x and z, unmeasured, unobserved. There is another U sub xy that is both affecting x and y. I'm just making the problem realistic, acknowledging that you are incapable to measure this guy. The system is not Markovian. Now it turns out that if you do transfer, I'm copying the data sets from the previous slides. This is the LA data set, the Z specific data set, same numbers. And this is the New York data set, observational study, P star of X, Y, and Z. Now, if you do the transportability analysis, you see that the causal effect of X on Y in the population pi star is the same reweighting by the P star of Z, despite of these bidirected arrows. And in some way, given that we have the interventional graph and the Z, these S variables is separated from Y, if you know the separation, I assume that a lot of people here know. If you don't, just ignore that for now. But eventually, this will be the formula. It's okay. In other words, it seems to be universal. Even if you have, or someone could believe, may be tempted to believe that it's universal. Now I would like to show another example. Suppose, which is almost always the case, that someone messed up and they forgot to measure the Z, the original Z that was age. Now age is latent. The Z that you measure, we call Z the proxy for age. Could be a language skill. Depending on the age, you have a different language skill because we are growing. There's some kind of monotonic, almost monotonic relation there. But anyhow, now assuming with the same, the question here is like, with the same data set, just doing the discretization, binning in the proper way, same numbers here. The question is like, same data set, what is the P star of Y given to X? Is it the case that the pseudo or the claimed universal formula is true? That's the departing point here, the question that I posed for this friend demographer, or the friend in the demography department. Now, note the following here for the collider folks. Note here that this variable square here, in reality, the meaning of that I didn't open up, but is encoding the source of heterogeneity. This encoding all the factors that are generating the f of z will be different than the f of z star. In reality, the p of uz different than p star of uz. But I call as the mechanism f of z. Now, note here that if you condition on z, we're kind of injecting, there is an open path from S to Z, Z to H that is not measured going for Y. Then condition on Z, as we are doing this formula here implicitly, in reality is injecting heterogeneity in your quantity. Then this is not what we want, because we're getting further and further from the truth. It turns out, you can also see that the collider has this abnormal behavior that if you don't condition on Z, it turns out that given that we're in the do X graph, that there is no arrows pointing to X here, there is some kind of sense of intervention, the Y is separated from the S, which means that in this particular scenario, the P star of Y given to X, I will just copy the PY given to X from the LA dataset. And the claimed universality was debunked. It's not true that this formula is universal. The guys are just doing it blindly. They got lucky in the first one, the same way that people get lucky with the back door. There's another discussion if you guys want later. But anyhow, then this is the first example that it is not true that is universal. Note here that both guys are pre-treatment. Z comes before X and Y, and here the same. Now, some people believe that this pre-treatment I should just adjust for. Not true. Here you should adjust for, in this different adjustment, by the way, but anyhow, you should adjust for, here you shouldn't adjust for. What about the post-treatment? Could we ignore the post-treatment variables? In this case, note here that if you ignore the post-treatment variables, Z could be a biomarker here. Let's just do the correct binning. We have the same data sets. Now there's a treatment that affects the level of the biomarker that in turn will affect the outcome. Should we ignore, can you ignore the post-treatment Z? Note here that the Z, they behave different between LA and New York. They have a different type of population there. Perhaps you have more Europeans here in New York than in LA. They have a different biomarker profile. Now, which means that if you ignore Z, in reality or in practice, you are adding the disparity to Y as well, or you're avoiding to have even the opportunity or maybe using this data here, because the two populations are heterogeneous. Now, it turns out that the correct way of combining these two data sets is neither A nor B. In reality, there is another way that you pick the pieces from these two data sets here. It's a different type of adjustment by the P star of Z given X. Now, the lesson here is that causal assumptions are required since the data doesn't impose enough constraints over the causal structure. And the results are causal or structure sensitive, meaning these two data sets here, that is the input of the analysis, doesn't allow or do not allow me to us to distinguish what is the true data generating model. They are all compatible with A, B, and C. Point one, the first part of the sentence. Second part of the sentence, if it's A, there is one formula. If it's B, there is another, the fusion formula. If it's C, there is a different fusion formula. Then essentially there is no way of avoiding having the graph in this case. It's a kind of proof by picture here, or as the title says, the transport formula is sensitive to the causal assumptions that we have. In reality, the relationship between the two domains. The assumptions is just our knowledge about this relationship. Now, I would like to move on here and just generalize.
Yes, just quickly, we have about 7 minutes left.
I'm counting 10 here, Paul.
Yeah, fine.
Okay, let's negotiate here. The 10, or maybe you give me more, 1 or 2, but anyhow, I'll move on. I hear you. Thanks. Now I just want to generalize what problem I'm really talking about. The problem is, there is a decision problem. Query that we have is P star of Y given to X. We have a causal graph or selection diagram in this case that is encoding the knowledge that we have about the problem, and we have multiple data sets. Now the question that we're research question here, paraphrase is like based on the current knowledge about the problem that is encoding number 2 and the available data sets that is encoded in 3 is the research question that is number 1 transportable or computable from the spare knowledge plus data. Now you have a transportability engine that you call. Sometimes we like to have a solution, sometimes you have, sometimes you don't have, as in life. If the answer is yes, as in the case that I showed before, it means that observational data in target plus experimental data in the source, that is the data here in the last number 3, implies the causation in the target domain. Then for, that's the result. Sometimes you get a no answer. I'll talk about that in 1 second. Now, I'll not read let me just read give the idea of the theorem. The theorem is just some type of syntactic, the type of formal results that you have. This is just the intuition that I'm trying to give. Paul asked, right, what are the kind of problems that you guys are interested? This is the kind of problems. The results that you usually get is some kind of theorem or algorithm. The theorem says that the causal quantity is transportable across the settings if and only if there is some type of do calculus derivation. I'll skip the do calculus derivation. This is just an example of the derivation itself. Go to the paper, Paul paper with me. We have discussion about this kind of derivation and what it means. But that's nice. Let me just give an idea here of what does it mean. Every time that you get a positive answer, the positive answer means the following. Suppose that you have the space here of all possible causal models in the world. This is just a space called omega, all possible collection of mechanisms. Now, this part of the space, this chunk here is the models that could be generated by G, compatible with your knowledge G. These models here in yellow are the models that are compatible with the distributions that are being induced. PV, observation distribution in the source, or observation distribution in the target, and experimental distribution in the source. Now there's an area here that is the intersection, that is in green. Now, if they have the same P star of Y given to X, we'll say that it's transportable. What I mean by that is, like, formally, for any 2 causal models encoding this unobserved nature N1 and nature N2, such that they have the same causal graph, that is the one that we are giving, the G of one nature N1 is equal to the G of the second nature, that is equal to G. And they have the same distributions, that is these ones here. I'm just saying P1 is equal to P2. I'm just copying here. These will imply that they have the same, this is observed, this is the data. This will imply that they have the same target distribution, Py given to X in pi star in the model 1 is equal to P in the model 2. Then that's the meaning of the transportability. They have this agreement here, which I usually say this is the kind of what I like to call the don't care statement. Then I'm allowed to not care about what is the particular collection of mechanisms. Because for all mechanisms that have these properties here is in blue and yellow, they agree with the answer. Then it doesn't matter what are the intricacies or the details that we have of the underlying structural causal model. That's the meaning of transportability in a kind of model theoretic for the mathematicians that are in the room, model theoretic kind of view of transportability. Now, is it always the case? I would just like to contrast briefly. That is not always the case. This is the graph that I showed in the previous one that we are able to get. Focus here, if you're not looking at the screen, look now. Note that the variable W is here. Assume that someone messed up and they forgot to measure the variable W. Then this is the causal graph that we have without the W there, compatible. Same data generated model. Now the W moved from the endogenous to the exogenous set. Now, is it possible to compute the P star of Y given to X in this data collection? I will not show, no, the answer is no. I will not show the derivation here because it's intricate, but it turns out that you can show these different natures that agree in the data and disagree with the query. Pictorially, I'm trying to contrast the positive one with a negative one, that some models that all these guys here agree with the data. But now some collection of mechanisms are inducing the green, some collection of mechanisms that are unobserved are inducing the red, and they are not distinguishable, which means that we cannot commit. We don't know what is true. Then that's the meaning of a non-transportability case. For sure, I'm just putting green and red here. There are infinitely many in reality. This space is fragmented. But anyhow, that's the idea of transportability. Personally, in the last maybe 3 or 4 years, I'm interested in the right side. I'm studying the negative instances because the positive are just positive. And we can just use the result. But anyhow, that's the idea. Now, second type of result, and I'm trying to move on here, is like we don't need to do the derivation through the do calculus. There is automated procedures to do that. You can input the selection diagram, that is this overlapping between the source and the target, and the algorithm will return the output if it's transportable or not. If the answer is positive, If you're in the left side of the previous slide, it'll tell you what we need to measure in the source and what we need to measure in the target. That is the green and the pink. If the answer is no, we can talk about that later. But anyhow, there is a good question here because it means that the translation of the no means based on your current knowledge about the domain, which may be nothing, as I said, just everything pointed yellow. Based on your current understanding of the domain and the data that you collect, things are too ambiguous, too bushy in order to disentangle the causality from it. Then we need to do something else, but we cannot make this statement at the moment. We do care now. But anyhow, those are toy examples. In reality, we're in a much more complicated type of setting. This is just one example of applied project that we are doing. I'm sure that people talk about a lot applied. I was trying to give it a big picture, but in reality, we are also interested. One of the reasons that I'm here, in addition to because Paul is here, but I would like to talk with you guys to have more examples and play with settings like that. I think they are throughout the economics, the business, and the social sciences. Then I'll be very happy to talk. But this is just one example in a domain that is medical domain related to ARDS, that is some kind of disease on the lung, in the lungs. But anyhow, I'll skip the detail. The idea is like, for sure, in a more bushy situation like that, we have some kind of automated transportability analysis for large-scale settings, leveraging the intuition that we have to these smaller settings. Now, I am almost concluding. I like just to mention a note that's a common confusion in the literature. And I have more 3 minutes or 2.5, I think. But the common confusion here that is people is messed up or unaware. They believe, let me start. They believe that randomized controlled trials are the solution for all problems, which is quite naive, as we already saw. All the dimensions are there anyhow. But let me show you one example, the simplest possible instance that I can think of that this is the case. So the world before randomization here is this one. When you have the treatment X affecting the outcome Y, we have a set of pre-treatment variables Z, age, sex, ethnicity, gender, whatever, right? Let's say sex, whatever, like religion and so on. And this is affecting X and Y. And then you have these bidirected arrows here that is these unobserved confounders affecting all pairs of all combinations of observed variables, XZ, ZY, and XY. Now, people would say, I don't want to engage in this type of exercise. It's too complicated to do the causal graph. Now, what I will do, I will buy my way out of the problem. I will randomize. Now, what randomization gives us? Randomization gives us, in the best possible scenario, unconfoundedness of the treatment X and the outcome Y. Meaning, in the best case scenario, we are able to remove any error that is incoming to X. Now, from this sample, then, all the variations of X that are left there are causal variations. Then this should be the do distribution. That's the intuition, graphical intuition of the experiment. Now, the Fisher was ingenious. That what people are saying now is completely the opposite, if I want me to be mild here. But now, the point is, you already have a feeling about transportability. Note here that it is true. Question, can you disentangle the source of heterogeneity or these variations across the populations in this particular setting, the right? Note here that this is the square, that is the S. Now, if you don't take Z into account, this is already, this S pointed to Z that directly affects the variations of Z, that affects the variations of Y. Then there is no way of getting it. The P of Y given to X comma Z, sorry, P of Y given to X is different than the P star of Y given to X because of this direct path here. Now people would say, let's condition on Z, because if I'm controlling for Z or accounting for the variations of Z, these may account for the sources of whatever, exogenous variations. But note here again that if you condition on Z, this variable S here, the square, you open up this collider here, that there is these two incoming arrows to Z. Then in reality, this implies that the P of Y given to X comma Z is different than the P star of Y given to X comma Z, which disallows us to compute the P star of Y given to X, the marginal effect of X and Y. Then the Z specific is not invariant, it's changing, which means that the P star of Y to X will also be changing. Then randomization tells us it's completely blind. is silent, tells us 0 about this guy here, then that's the point, or the lesson. Even if you have a perfect RCT, one still needs to do the transportability exercise. This transportability theory is unavoidable. In other words, it's unavoidable to place causal inference even when you can conduct experiments. And number one. Number two, that's a much harder exercise even when you are doing Rubin, Robbins, David, and Pearl. That is from observations. Why? Because here it looks innocent looking, very pretty face here, this diagram. But these diagrams are much stronger than the causal diagram, because in reality there are two causal diagrams and you are trying to compare them. Their assumptions are super strong, but they are needed. We can prove that they are needed. Then there's no crime. There's nothing you can do about that. Then this is just the baby example here to discuss about very naive view. Theory or causal inference, as we understand, unavoidable in general. There is no way we can go around it. I'll be happy to elaborate. Can I give just one summary of my lab and I go to conclusions? Paul, do I have more 1 or 2 minutes?
Okay.
Okay, then let me just give a share here if you have people interested in collaborating or visiting or even have postdocs. This is the picture here of the Causal AI lab, Causal Artificial lab, what we have been doing. The key observation from the lab is almost like the structure of DNA. There is this underlying collection of mechanisms that are there. They are there, they are unobserved, but they are there. And this is the first. Now, once we acknowledge that seems trivial, still there is a lot of resistance to that. Now we can try to explain what are this collection of mechanisms. And then there is the whole topic of what we mean by explainability, which means effect identification and decomposition, bias analysis, fairness analysis, robustness and generalizability. We talk about transportability and so on. Libraries are a lot of grants written on explainability, but not from this perspective. We are trying to explain this underlying opens nature's black box and try to understand what are this collection of mechanisms at some level, which granularity we can get. That's the question here. A huge amount of work here. We have many papers. The other side of the coin that we're trying to understand, someone could say, Elias, I'm a pragmatist. I think it's very beautiful and nice what you're saying, but I don't care about understanding nature or anything like that, human beings. I'm just trying to optimize here my bottom line. Then me too, in some way, depending on the hat here that we are, then you may care about the decision-making here. We are embedding the agent in the system that is running through this collection of mechanisms. Now, there's huge literature on reinforcement learning, randomized controlled trials, personalized medicine, decision-making, and so on. Again, libraries written about that, not from this perspective that we're embedding the agent in the collection, in the environment that is represented as collection of mechanisms. Check it out, the CRL, Causal Reinforcement Learning, Causal AI. I talked for 3 or 4 hours just about this particular view that I'm talking here. Now, there is some interaction among them, obviously. As much as you understand about a certain system, okay, I got it, Paul. I'm done. For as much as you understand about the system, we can do better, more surgical and precise interventions. And if you are blind, but you start doing randomization, eventually you are learning about some parts of the system. We are very interested about applications, education, software. Today, I talk about the data science part, that is like how to do principle, be able to get this label scientific, it's not astrology, principle inferences from large data collections. Some days I'm talking with my other hat in the right sides about how to build AI or principles and tools for designing robust and adaptable systems. Now, my conclusion here is like going back here, drop me a line if you're interested in this mission that we have been pursuing for the last 10 years around. Now, causal data science, going back here, causal data science, principal way of combining substantive knowledge about the phenomena under investigation with data to generate causal explanations and better decision-making. Key insight here, words good, no all data is created equal. Most modern data collections are messy and plagued with systematic bias that need to be understood first and then controlled such that causal claims can be made. Causal data science solves long-standing challenges in the empirical and data-driven sciences, including confounding bias. So I go into dimensions: confounding bias, selection bias, measurement error, generalizability, and data fusion. I'll be happy to take questions. Thank you. Appreciate it.
Thank you very much, Elias. Very interesting talk, and sorry for showing you the red card, but I know that as a fellow Brazilian, you also like soccer, so that should be fine. Yeah, so we already have questions popping up, and that's, yeah, I see the first two hands for the Q&A. I think Andrew was one of the first. So you should be able to ask.
Can I see, 1 second. Let me try to find my mouse here.
Andre, are you there?
Do you want to read it? The first one at least? Oh.
We can have the question via audio, actually. I can unmute the people, but it seems that Andrew is not there yet.
Okay, I have my...
So then let's maybe move over to Naftal.
I have one here in the Q&A.
Yeah, we take that afterwards.
Okay.
Okay, can you hear me?
Yes.
Oh, perfect. Great. So thanks so much for your talk. I really enjoyed it a lot. So it seems to me one use of the transportability framework that you haven't mentioned is that if you start with a selection diagram where you have a quantity that's not transportable, there are cases where by measuring additional variables, you can get a transportable model. So if you have X causes Y and there's a bidirected arc and an S node into Y, so that's going to be a very simple non-transportable case. But then, of course, if you measure a mediator and you make additional causal assumptions, then it might be transportable. So my question is whether this aspect of transportability has been formalized in any way. I mean, it seems like it's inspired by transportability, but as far as I could tell, the framework only applies to cases where you have the same variables across the model.
Yeah, that's a good one. I would say that this is usually put as a challenge. I don't know if you have a, thanks for the question. The two quick notes. First, we don't say that the model is transportable, right? We say the query is transportable from the data plus model.
Right, yeah.
And this is important because the second point is like, in other words, it's contingent on the current understanding that we have about the system that is the model and the data that you are able to collect, that they are kind of aligned in some way. There's some notion of compatibility between model and data. Now, the case that you are saying is a case like, suppose that A here, we don't, let's say that Z is not here, then the one that I showed, I think I didn't show, but there is, if you marginalize out Z, in reality, this arrow from S will point directly to Y.
Mm-hmm.
Now, this will be the model that we have. Now you're asking, oh, perhaps you got the way that I see the question, you got a no answer. Now, yeah, perhaps you can no answer, give transportability answer. Now, if you, exactly what you said, now, if you tell the agent, oh, you have the possibility of measuring the mediator, that's called Z, in between X and Y. Now you kind of unfold the model from this side here, that there is a Z not here and the S pointing to here, to this side here. Now you can, another step of transportability theory to be evaluated, can you compute the transport formula from this case? The answer from the theory in this particular model is yes. Then what we're saying, two answers. It is accounted in the theory because the theory is just given a model and given data, you have the decision problem. Then you can give me whatever model you want from a whatever model you want. That's what is developed. Then the answer is yes, it is accounted. Now the no part that is not accounted, we don't know how to do. It's an open problem. We are thinking, but I think there's a lot of huge amount of work that could be done about how to navigate in the space of models. It's kind of the outer loop that we have outside each particular transportability decision. When you have this no answer, how can I decide in some way to open up and go to this, from this model here to this one here? Then this one is not understood. Then this is the answer that we don't know how to navigate in the space in the model in a clever way. You can be, obviously you can be naive. And this is what we do. What a clever data scientist will do is like be resourceful in the sense that what else they can measure or which other kind of experiments they could do when they get a no answer. For sure, you like to be clever or systematic or algorithmic about that. We don't know how to do that at the moment. It's a very good question or problem.
Okay, thank you.
Thanks, Naftali. And I will reply to you. We need to talk offline.
Okay.
I appreciate it. And I'm sorry for not replying.
No worries.
All right, we have another question in the Q&A by Matt Bogart. Matt, you should be able to ask your question directly. Are you there, Matt? Because your question was a bit long to read out. Okay, then I think we move on. Maybe
what I understood from the questions, like, can data fusion works in the corporate business when you have multiple interventions and so on? And the answer is, yeah, in principle, there is nothing that is hard-coded about this. Is the whole point of having multiple interventions, multiple populations, and disjoint kind of data sets in time series that I think he's referring to. I'm reading very quickly here. In principle, some need to dig deeper in the particular setting to see if the solution is nice and polished, or if a little bit of manual work is needed.
Okay, then we can move on over to Daniel Grünbaum has a question, so you can unmute yourself.
Hello. Yes. Thank you, Elias, very much for this great talk. I'm very, very interested in causal reinforcement learning. I think that's a really exciting area. And I was asking myself, what is the main obstacle that is holding people back from performing causal reinforcement learning in all sorts of scenarios? Because as I understand it, you can use observational data if you know what the underlying causal model is, and then use this basically to simulate the environment for your agent and get the possibility to train your reinforcement learning agent without having to do expensive experiments or simulations or whatever. Do you think it is most about you cannot formulate the causal model precisely enough, or is it that you have so many techniques chained one after the other in this approach that in the end the errors accumulate too much, or is it just that people do not know about it yet?
Yeah, that's a good question. It's kind of social question, I guess. Two things. One is like about having or not having the causal model. Even the current generation of RL, the non-causal RL, if you want to create a line here, is not the approach, but the part that is less sensitive to the causal or sensible to the causal type of work. They are implicitly assuming a causal model. All literature on multi-arm bandits, Markov decision process, POMDP, MDPs, POMDPs, and so on, they just have a hard code that I like to call a template-based causal model, then which allows them to do something and don't allow them to do others. Then, and the tendency is to try to hammer more, or whatever, do more of the same that you are used to. Then that's but the causal model is there. Then there is no such thing as non-causal model. The question is like, is it implicit or is it explicit? Because the environment is causal. And you are embedding the agent there, and the agent is trying to do interventions and maximize some reward based on their own action. Then the whole setting is very causal. Now, the whole literature, starting from Sutton and Bartlow and so on, is based on these implicit models. Then this is topic one. Mostly, not entirely, but most traditionally, that's a literature that is going on for the last 40 years, 30 to 40 years. Now, these results are recent, I would say. Then I think many people are not aware of them in the RL field, but they are super interested. I just gave a tutorial, a 3 or 4 hour tutorial 3 or 4 months ago in the major ICML, the major machine learning conference, because people are trying to learn about what is the CRL, what's the causal reinforcement learning. Then I think with time, they will start learning and start using these results. Now, my third point here is just the part that is hard. For sure, there is a loop there that we're trying to learn the causal structure or refine. As I said, they already have it. Refine the causal structure that is the quote unquote mind of the agent. And that's a non-trivial problem. But still, I think it should be part of the RL loop about we are not just trying to optimize the reward or to pick the actions X such that we have the highest Y, but there is some kind of trade-off between understanding a little bit more about the underlying system, such that in the future, you could do more precise interventions or even to lead to higher rewards. This is a kind of obvious, kind of natural flow here, historical. The reasons I think that's my feeling. given this a social question. Yeah, I don't know. Does it make sense to you, Daniel?
Yes, thank you very much for this insight. I'm really looking forward to what is happening in the near future with this field. Thank you.
And Daniel, just one more note, but for the others, because people, as I said, people are very interested in the CRL. Check crl.causalai.net. Is a website that we just created for the CRL, given that there is a lot of interest, and we are trying to classify the new and different tasks that are not acknowledged, but they are pervasive in RL settings, that we can see them very easily when we have causal lenses. Then, and we have, whatever, check it out, crl.causalai.net. Thanks, Daniel.
Yeah, thank you, Daniel. Next up, we have Wouter. Wouter, you can ask a question.
Hi, Elias. Thanks for the presentation.
Hello.
So my question is on applications. One of the common heard objections against these DAGs is that they look very pretty for toy problems, but once you move to actual applications, then they can become pretty messy, as you already showed. And I was just wondering, do you have experience? Do you see many actual applications where the DAGs are used? They lead to something that can actually be estimated from the data. And also, like, one of the tricky things might be that even though DAGs are great for communicating assumptions, that once your DAG becomes very complicated, it also becomes less and less of a thing to communicate because it's so hard to read. So have you seen any successes using these DAG methods for observational causal inference for actual applications? What do you think about those?
Mm-hmm. Thanks, Walter. Good to hear from you as well. A long time no see.
Yeah.
I would say, personally, I will not, today I will not, let me do more the philosophy, the general idea. I will not pick applications here and give you a list. And I think you guys have been discussing that. But I would like to pick in a fundamental problem, that point that is misunderstanding about the DAGs. The DAGs, yeah, they have this kind of pretty face or kind of friendly face. But in reality, we don't, meaning whenever we scale, DAGs are nothing more than the encoding the invariances that we have about this underlying collection of mechanisms. Now let's try to unpack. DAGs are nothing more than encoders of the invariances with respect to the underlying collection of mechanisms. Then sometimes I don't know the DAG, sometimes I know the DAG, sometimes I know a fragment of the DAG, which means that sometimes I know some of the invariances, sometimes I don't know them. Sometimes I know all of them related to the set of observables, in this case, X, Z, and Y. Sometimes I know just a piece of them. Then the discussion is misleading when you say, oh, can you do with DAGs or without DAGs or what? Meaning, the invariances are there. The DAGs is just a language to make them explicit. Now, there's kind of theoretical results on how this links with other possible ways of encoding this type of assumptions. Another result that we can see, like the assumptions are needed. There's some type of completeness results that you cannot do some types of inferences if you don't have this type of assumption. Then it's almost like an inevitability and a maturity from us as a community, including me, obviously. But like, man, this is just needed. There's no way that we can go around it. Then do you want to try to make it explicit? Do you want to try to understand the limits of the inferences that we can make whenever we don't understand fully the system in some way? Again, that is already a coarsening. We are moving from physics, that the guys are trying to get the probability, the structural functions, the F is equal to MA, and the border conditions, that is the probability of exogenous. We are moving from there. We already gave up on getting the description of the system at this level of granularity. Then the DAG is just moving from there to some kind of coarsening. Now the question is like, are there mature discussion? Are there other types of coarsening? Very interesting, by the way. In the last 1 or 2 years, we're studying that. Are there other types of coarsenings of the structural mechanisms that are not the DAGs? We have some works in you can go to the lab website that we're doing some type of equivalence class of DAGs. If you want to be kind of more data-driven or some kind of, whatever, some kind of compromise between substantive knowledge and being data-driven. Then you don't get one DAG and you don't get entirely from data. You have some kind of mix between them. But the point is like, I would just like to make this note, that is like, the DAG is always there. And if the system grows, I show some example that it looks like a mass. this system with, I don't know, dozens of variables. Where is it? Like that. Yeah, it's true. No one is one shot trying to understand this whole system in the way. And this is not the point. The point is like, this is just, now it's not more about friendliness. It's about, this is just explicit encoder. One thing that you learn as well is not only explicit, but it's parsimonious. And I'll take it offline, but there's a discussion in the areas about, should I encode the joint probability distribution explicitly, or should I try to find a data structure that allows us to encode just the constraints over this probability distribution? And this is how it started Bayesian networks literature, or the Markov random fields literature, MRFs. This started in the 80s, noticing that it's totally impossible, because it's super exponential, to encode this type of probability distributions explicitly. Then the whole literature in graphical models is started about, how do I find a parsimonious encoder for these distributions? Moving to causality, we have other assumptions coming in that is not only parsimony, but still, the idea is the same. We're just trying to be mature and honest about the assumptions. And my last note here about that, systems like that I'm saying, and by the way, I know that you are on board, I think, or you understand this, but systems like that also, it allows us, when we are talking with people, no one is understanding them in one shot, but usually the exercise is about, let's think about them locally. The model allows us to think about them locally. I don't need to think about the 50 variables or 100 variables. The system is bigger, by the way. 100 variables in one shot. Maybe the physician or the social scientist can talk in chunks, and then you can discuss these 10 variables in one shot, and then try to connect with another 10 variables and do that in clusters. But in some systematic way, the graph is just leading to some kind of glue, allowing us to put the pieces together. But anyhow, I think is that idea. Let's make it implicit, or I'm for making it explicit and not leaving it implicit. But and I haven't seen any successful application when we left that implicit. It's just kind of astrology at the moment. But then this is what I'm advocating for here.
Yeah,
Let's
totally with you.
Mm-hmm.
Okay, thank you. I see there are many more questions. I apologize to everyone who still has a question left, but given that we only have 3 more minutes, I want to ask one last question to you, Elias, because the question that we put out when we put out the call is what's next for causal inference? And what can we do to push out causal inference more into practice, into medicine, into business? So what are your thoughts on that? What are the next steps in the upcoming years?
In 2 minutes or?
Yeah, 3.
Okay.
Top priority.
There are challenges all over the place, by the way. One note that I will start is like, some people see some of this talk or some talk and they say, oh, Elias, everything looks so pretty and fitting in place. It seems to be done. And my point is like, not at all. I'm just deciding to show things that are more polished, obviously for your enjoyment and to try to get you to help us to work on the field. In reality, there are challenges all over the place. And I will give you an example that we have been spending the last 1 year, and maybe you can help. That is, many of these formulas that we get comes from the causal analysis, but now after, like, we get a formula like that on the bottom. And the formula is true, obviously, if the model is true, formula is true. It's a tautology here. But the question is like, how do we estimate that from finite samples? Then turns out to be really, I'm putting the number 1 there, the Kolmogorov, Poisson, Bernoulli, Kolmogorov as being done, and we are building on that. But once we come later and close the loop, now I need to really estimate that at the end of the game, at the end of, after all. Now, turns out to be challenged. For sure, you can be naive or less causal and just hand in this formula or something like that to the, where's my mouse? Disappear again. But you can get this formula at the bound and hand it to some statistician or machine learning person. But in reality, there is much more information that in the causal graph. Then you can at the same time leverage these constraints that I was talking with Walter earlier to be able to estimate this guy efficiently. Then check our work in New Rips this year is about how to design machine learning algorithms based on the ERM, empirical risk minimization, to try to estimate beasts or animals like that. They are quite challenging. This is just the first, or very few papers already. I can count on one hand what we understand about this type of estimation. Then I think it's an open challenge, obvious one. There are many. Another one is like, as I was talking Walter as well, sometimes you don't have the causal graph. Maybe you can have a collection of causal graphs that are equally believable. Then the question is like, how do you connect these graphs, or how do you cluster these graphs, and how do you make sense about the collection of graphs plus the data set, and what can you say about the inference? Carlos, earlier today, Carlos Sinelli, I think he was talking, I was not here, but he was talking about sensitivity analysis. Then I think this is a good topic, how to do sensitivity. There's sensitivity analysis challenge all over the place. He has an example there that's a very cool piece of work. Many others about sensitivity analysis when you have two models. There is the broader theme about when you have an equivalence class. Look in my website for equivalence class. We have maybe a few papers, less than 10, I would say. But anyhow, it's a topic that you like to understand more in the next, I don't know, 2 or 3 years. My last bullet here is I think very interesting about going towards applications in this online decision-making systems that is related to the CRL, the causal reinforcement learning that I was saying. Usually experimentation is expensive, even in these settings. I get it from friends. I never thought that I would heard that, but from friends from Google or Facebook or these places that have possibility of doing huge scale, huge amounts of experiments. And they are sometimes they are talking with me informally that we are running out of people because we have so many experiments that we are trying to run that there is not enough people such that we can get some reliability in some of these estimations. But how to combine data sets in the settings across different experiments that they have, and more broadly in the CRL setting, I think is a very good, would be profitable, scientifically interesting and profitable in terms of business and applications. And is an area that I would be watching for. I think those 3 is enough, or you want more, Paul?
I'm sure we could talk for ages and hours more, and we'll do that at one point. But at this hour, it's 8 in Central European time. We have to conclude. And I thank you very much, Elias. It was extremely intellectually inspiring. I thank all the participants who joined the Causal Data Science meeting. I think it was an extremely successful first iteration, and I'm sure we're going to do something like this in the future again. I will just post, for those of you who are interested, in the chat a little, given that it's much less social, these online conferences, but we can have a little after our hangout if you want to meet us in the Zoom. I posted the link in the chat. Just copy that to your browser and we will still hang around for a couple of minutes. And thank you again, Elias. For you, it's only lunchtime, so half the day ahead still. And
thank you, Paul. Yeah.
See you again.
Thank you, guys. Appreciate it. See you. Bye.
Thank you. And see you all.
Thank you. See you.